And we're back. Welcome back and happy Tuesday. Today we're going to pivot our discussion to focus primarily in this module on issues surrounding error, the coincidence between the unknown target function and our working hypothesis, which results through search, the action of the learning algorithm results in the final best hypothesis. So we talked about transforming your representation, and you're given, in the example we carried forward where we last left off, a non-linearly separable data problem. In this case, the geometry of feature space is such that we had points from one category, the blue points, were towards the center of the representation, and points from the other category, the red points, were towards the outskirts, if you will, of feature space away from the origin center. And we applied a transformation, phi, a so-called phi function, a sort of polar transformation, and it changed the geometry. Those points, the blue points that were closer to origin in the unadulterated feature space representation, in the new representation, they were closer to origin, the lower left-hand corner, radially, and those points that are further away from origin, the center of the representation in the first frame, were higher up and to the right, further away from origin, the lower left-hand corner, in our new representation. And now with this transformation, our blue points and red points become linearly separable, and therefore PLA, as we know at this juncture, can find the final best hypothesis that perfectly coincides with the unknown target function. So let's look at nonlinear transformations more generally. Now, we have our original data set where each point is a point in D-dimensional feature space representation. And this is our original input space. And you can think of each of these xi vectors being drawn from R super D. Now, of course, when we learn, that hasn't changed. We augment our feature vector with dummy variable x naught, and we take our weight vector w and we add in w naught to absorb that threshold, minus t, as we had done in our mathematical expression, resulting in w transpose x. And so the result of our phi function operates on the features in our original representation. And this phi function changes the geometry. It changes the geometry, resulting in a new feature space representation we'll call Z. And we'll call Z feature space, but we'll call the original representation, we'll call that input space, the unadulterated representation. And so this phi function changes the geometry in our input space, resulting in a new geometry in what we call Z space or feature space. And so now we take this transformed data and we learn a linear hypothesis, a weight vector W, but that W is in Z space, not in our original input representation X. And so when we transform the data, we run this phi function on our inputs, one data point x little n at a time, and it results in a corresponding Zn, our point in feature space, which is the new value for that feature vector xn. And so if we have big N, many vectors, x1, x2, x3, x4, so forth, that's going to result in, through action of this phi function, a Z1, a Z2, a Z3, and so forth. And so corresponding to a particular data point, when we run that phi function over the data point, we have a resulting Z point in feature space. And so we start out with our original input, our data point, in input space. We change the geometry by application of the phi function, our transformation, and each of those data points xn results in a corresponding new version of this data point we call Zn in feature space Z. Okay, so now then, when we compose our linear hypothesis, our weight vector, we're going to call this weight vector W tilde. Now, this tilde is going to connote that, yes, it is a weight vector, but this particular weight vector is in feature space. It's in Z space. And so now, when we run PLA algorithm, after transforming into feature space, we get a final best hypothesis. We'll call that G tilde. And G tilde is going to be that result from running PLA, that hypothesis that most closely matches the ground truth target function, which has not changed. It most closely matches the ground truth target function. It's in assignment of labels to these Z points in feature space. And so when we apply that phi function, we change the features, but we do not change the label. The labeling carries forward. So we get this final best hypothesis in feature space, in Z space, G tilde. And G tilde is just W transpose Z, where each Z is one of those points in feature space. And so we use W tilde, and the points corresponding to the X points are the Z points. And so our final best hypothesis, G tilde, evaluated on a new input space in feature space, is just sign of W tilde transpose Z. Now, of course, we said if this is a nonlinear transformation phi, we get the benefit of a nonlinear decision boundary, nonlinear hypothesis, but we only pay the cost of a linear hypothesis, that PLA update, that search in Z space. And so if we wanted to go back to the original input space representation, we absolutely could do that. How do we do that? Well, if we have an invertible phi function, we just compute its inverse. And we can take this phi function, compute its inverse for each one of the data points that would give us the resulting points back in the original representation. But if we look at this final best hypothesis G, we can actually draw that nonlinear decision boundary in the original representation. How might we do that? Well, remember, sign W transpose X, if it's greater than, it's one data point, the positive examples. If it's less than, it's the other examples. But the linear model itself are all those values in feature space Z for which W tilde transpose Z is exactly equal to 0. So if we sample and solve for those values Z for which W tilde transpose Z, our final best hypothesis, is equal to 0, then we can produce that, take the inverse of those points Z and produce exactly this nonlinear hypothesis. And so if you are given a new input in input space, X, you can classify an X space using your transformation. Well, this final best hypothesis in X space is nothing more than G tilde evaluated on this phi function over that new input X. Because if we want to sign W tilde transpose Z, well, we said Z is equal to phi function evaluated on the corresponding X. So now we can use this hypothesis in Z space, W tilde, with our phi function to actually take an input in our input space representation, a new one, and compute G of X new is equal to G tilde of phi of X new. Okay, and so this G tilde is nothing more than this W tilde transpose times phi of X, and we're taking the sign of that resulting score. And that's our classifier. So absolutely, you can take this hypothesis, this final best hypothesis that you learned in Z space, and use it to evaluate new inputs in the input space representation. Okay, so let's take a look at relationships for this transformation. For every vector X, you have a corresponding vector Z. Now, this phi function, it can be a one-to-one expansion. And so we see that in the previous slide, we're going from a two-dimensional input space representation to a two-dimensional z-space representation. It can also be contractive, meaning that you decrease the number of dimensions as a result of applying this phi function. It can also be expansive. Now, because of this, we make no assumptions on the form of this phi function. And because of this, we say input vector x through our phi function is mapped to a point z in feature space in z space, and that z space has dimensionality. And remember, we have the augmented vector z naught, z1, up to and including, and we say z d tilde. Now, of course, the original dimensionality in input space representation was little d, and the dimensionality in z-space representation we're calling d tilde. Now, d tilde could be equal to d tilde could be smaller than z, that's a contractive mapping. D tilde could be greater than d, that's an expansive mapping. And so for each one of our input vectors in our input space x, x1, x2, x3, up to and including x big N, for n many data points in our data set, we're going to have a corresponding z. So we're going to have a z1, z2, z3, up to including zn. But we find that the class labels do not change. We don't transform the class labels. So the class label y1 for the first vector, y2 for the second vector, and so forth, are the same class labels y1 for the first z point in feature space, z1, the second one, z2, it's y2. Those class labels do not change. Okay, and in this, of course, there's no weight vector for the input space representation. The weight vector that we're learning is in z space, our w tilde. And so w tilde is of rank d tilde plus 1. So we have that w naught, that doesn't change, that dummy variable that absorbs the threshold. We have w1 through w d tilde. And of course, our hypothesis evaluator, final best hypothesis in our input representation, g of x, is just sine w tilde transpose z, where the z we obtain by our phi function evaluated on that x. Okay, so this is our mapping through transformation in the set of relationships between our feature space representation and our input space representation. It's really powerful and it allows us with simple PLA update, linear model, to get the effects and the benefit of nonlinear models without paying the cost. So let's take a look at error and generalization. We carried forward before this anatomy of a learner, and we said these red boxes are aspects of a learner that you had no control over, and we motivated this with the credit approval classification problem. We said that those black boxes, learning algorithm hypothesis set, are things you do have control over, and the action of this learning algorithm is to search through the space of hypotheses, and when it halts, you get your final best hypothesis, the learned credit approval problem. And so what is it meant when we say we're trying to find a hypothesis that approximates our unknown ground truth target function? What does it mean? Well, we need some measurement of that coincidence between our working hypothesis, H, and our unknown ground truth target function. So we need some error measure between our hypothesis, our working hypothesis, of which the final best hypothesis is a working hypothesis. It's the best one that most closely approximates F. We need that error measure between H and F. And so since we have our training inputs, our historical data, our data set assuming we have size big N, so we have x1, x2, x3, up to and including big N, we measure the so-called pointwise error. We measure the error between our hypothesis, H, and our unknown target function, F, at each one of our in-sample points. So said mathematically, we say E of H of x and F of x. This error measure is parameterized by two functions, our hypothesis H and our unknown ground truth target function F. Now, at this juncture, we've seen different pointwise error measures. we, in regression, saw the squared error measure, and that was E of H and F is just the difference, the square of the difference between H of X, our hypothesis evaluated on X. And remember, for regression, it's a real valued output. So we said that difference between H of X and F of X, we square that difference because we care about the magnitude and not the direction. For binary classification, this is where you have binary category, +1, -1, so-called positive examples. And the negative examples, we said our pointwise error, E of H and F, is just the indicator function for H of X not equal to F of X. So what does this indicator function do? It returns a 1 whenever they are not equal, whenever this condition is true. Otherwise, they return a 0. So what does this binary error classification do? It counts the number of errors, and you use that to compute an error rate. Because if, in the case of regression, H of X coincides well with F of X, well, the squared error losses are going to be close to 0. If we have a classifier and H of X coincides very well with our unknown target function F of X, we're going to have a lot of 0 indicator functions, and the error rate is going to be closer to 0. So we compute our error measure by averaging over these pointwise errors across our set of in-sample points. So for in-sample error, En of H and F is 1 upon n times the sum. N goes from 1 to big N, the number of in-sample points we have. Our pointwise error, H on X with F on X. Out of sample error, we discussed this idea of a probability distribution as being responsible for giving you the feature vector instantiations that you have. And these are feature vector instantiations that live outside of your sample. You have not seen them yet. And because it's a probability distribution, we can't take the average, we take the probabilistic average or the expectation. So our out-of-sample error of some hypothesis H is the expectation with respect to that probability distribution governing the sample vector instantiations, that expected pointwise error between H of X and F of X. Okay, so these are the ways we measure error. We measure in-sample error using our in-sample points, and out-of-sample error by expectation using that probability that gives us our vector instantiations. So when we look at this, well, the sample data we see comes from the distribution, the same distribution that gives us our out-of-sample points. So we augment the unknown in this anatomy of a learner with another edge that goes from that same probability distribution, giving you the out-of-sample points X that goes into the final best hypothesis. Because at the end of the day, what you're after is a final best hypothesis that performs well out of sample on new data points. But you're using those examples that you do have, training examples, from the same probability distribution in order to find a suitable G of X, one that strikes the right balance as prescribed by the union bound on Hursting's inequality. And so it's really, really important, this edge, to ensure that when you have a learner that you're building, that the distribution that governs your training data is the same distribution or as close to it as possible as that governs your out-of-sample data. Okay, so let's look at more how you select an error measure. Now, with this pointwise error, in the case of classification, we said it was an indicator function, E of H and F, is an indicator function for H of X not equal to F of X. Now, in this case, this treats all kinds of errors the same way, but that's not always the case. And here we're going to look at considerations associated with how you select an error measure when you build a learner. So let's imagine the following scenario, and this is in the book, Imagine you have a fingerprint scanner, and this fingerprint scanner will sample your fingerprint data, and there's a fingerprint example, and it inputs it, and the ground truth target function outputs a +1 if it says, yep, that fingerprint really is you, or -1 if it says, nope, it's not you, it's an intruder. Now, if we look at the following matrix, this is a so-called confusion matrix. It depicts all the different ways your learner can be confused or make mistakes. And so here along the rows, we have the outputs of a hypothesis, +1, -1. And here along the columns, we have the labels associated with the ground truth target function, +1, -1. And so anything for the first column represents ground truth as a +1. Anything for the second column represents ground truth as a -1. Anything in the first row is what the hypothesis outputs for a particular input X. Likewise, anything that's in the second row corresponds to the hypothesis saying -1 for a particular X. So if we look at those entries in our confusion matrix along the main diagonal, those represent all of those cases where the hypothesis agrees perfectly with the ground truth target function for a particular input. So this is pointwise error we're talking about. Now, in the upper left-hand corner, well, that's no error. The ground truth target function said it's you, so the fingerprint, and the hypothesis predicted, yep, it is you. They coincide. Likewise, in the lower right-hand corner, the ground truth target function said it's an intruder, and the hypothesis also said it's an intruder. And so we have correct output from our hypothesis. It coincides with the ground truth target function for those entries along the main diagonal in the confusion matrix. Let's contrast this with the off diagonal for the confusion matrix. If we look at the upper right-hand entry of the confusion matrix, we see that the ground truth target function says this fingerprint input, that's an intruder, but the hypothesis has said it's you. That's a so-called false accept or false positive. Likewise, if we look in the lower left-hand entry of the confusion matrix, the ground truth target function has said, yes, that's you. This fingerprint data, that's you. But the hypothesis has said, nope, it's an intruder. That's a false reject or so-called false negative. So if we look at this, there are two types of errors. There's a false positive, a false accept, and there's a false reject. And so depending on the application for which you've deployed your learner, you might not want to consider both types of errors, false positive and false negative, false accept and false reject, the same way. So let's think about an application for, say, customer loyalty. You go into a supermarket, you buy some goods, a number of them are on sale, you scan your fingerprint at the payment terminal, and if you are a member of the customer loyalty program, you get the discount. If you are not a member, you're an intruder, you don't get the discount. So let's take a look at what happens in those scenarios. Let's imagine that ground truth that you are a customer and there's a false reject. That's the upper right-hand corner, rather upper lower left-hand corner of the confusion matrix. Now, what happens? Well, you've been a loyal member of this market. You're in the loyalty program. You go, you buy your items, you scan. Boop. Nope, you're an intruder. You're not a member. You don't get the discount. So you start getting irate. What are you talking about? I'm a real customer. I deserve my discount. Scan it. Nope, you're an intruder. So what happens? The customer gets irate if there's a false reject, a false negative, the lower left-hand corner in this confusion matrix, lower left-hand corner entry, and this customer walks away. You lose a customer. And so now the market, because of this false reject, has lost a customer, never again to make revenue from this person for a really, really long time. Was it worth it? No, it was not worth it. The converse, well, the false accept is not so bad. False accept, someone who's not a member decides to go shopping in this market. This person's not a member of the customer loyalty program. He or she gets grocery items, walks up there nervously, scans a fingerprint, blip. You are in the loyalty, you get the discount. Great, wonderful. So you've just given away a discount. Well, this person's happy, but you also have their fingerprint, so you can find them later. But that being the case, this person's happy, and it's not so bad. You gave away a discount, and you shouldn't have. It's not as expensive as losing a loyal customer forever. And so in that particular case, if we look at the pointwise error, for this scenario, the false reject is much more detrimental in this application. And so in that case, when we look at how much error we associate with a false reject, we make it hurt more. It's more units of error for false reject than a false accept. Here we see the false accept entry, the upper right-hand corner of entry of the confusion matrix. It's only a 1. So not all error is the same. And when you deploy your system, you can set your pointwise error measure to make it hurt more for your model, and that encourages your model, your learning algorithm, to select hypotheses, in this case, that really try to stay away from false rejects. Okay, so let's look at another application, access control. Suppose you have a fingerprint scanner, and this fingerprint scanner allows access to a room filled with all sorts of secret, sensitive information. So if you have a false accept, an intruder comes in, scans a finger, and you belong. All right, well, that corresponds to, we said, a false accept, the upper right-hand corner. So what happens? Someone who's not allowed access to those sensitive information sources inside that room now has access. That's very catastrophic. Bad things can happen. In the case of false reject, somebody who really should have access scans his or her finger on the scanner and says, nope, you're not allowed in. And you say, well, wait a minute, I'm supposed to have access. They scan the finger again and again. Now, in that case, we refer to the lower left-hand corner of our confusion matrix, and a false reject can be tolerated. Well, the employee is still paid to be there anyways. It's not catastrophic. Now, in this case, the converse is true. The false accept results in a very bad thing happening. So in that case, you would make the pointwise error penalize a very large amount in the case of a false accept. So, for example, we might have 1,000 units of error for the false accept and only 1 unit of error for the false reject. And this will guide your learning algorithm to select hypotheses that really, really dearly try to avoid false accepts. And so this says that not all error is equal. And when you design your learner, you should consider how and what the error means for the application. And so the machine learning system's user should be allowed to specify the error measure, what is more detrimental, and this is a deployment issue. You should still expose control knobs, because it's not enough to say all error is the same. You need to think about the application. Now, of course, there are other methods for determining what your pointwise error should be. In some cases, maybe the error is not easy to craft. And so you might make certain assumptions, things that are plausible, such as squared error, assuming that you have Gaussian noise. And that's just a convenience to say, okay, well, the error is kind of difficult to conceptualize, so let's make this assumption. This is believable, and it's applicable to the problem, so we're going to go with this because it makes it feasible to implement. And then there are other methods where you choose a friendly representation of pointwise error. For example, having a closed form solution that might be amenable to convex optimization, right? So this is for mathematical and mechanized convenience. And so if we augment and include our pointwise error in the anatomy of a learner, this pointwise error straddles between our learning algorithm A and our final best hypothesis. It's used to guide the learning algorithm in a particular way to favor hypotheses and ultimately a final best hypothesis, because it's this notion of best that has desirable properties associated with it. So this pointwise error measure is something you control, so it's in black, and it has one arrow going to the learning algorithm and the other to our final best hypothesis that approximates our ground truth target function. And so the target function itself, if we turn our attention to it, it's not always a proper function. Take, for example, for the credit approval problem, you might have two customers that have the identical information, years in residence, salary, years of education, and so forth, but one turned out to be a bad credit risk and the other a good credit risk. So you can have two outcomes from nearly identical or precisely identical customers or input vectors. So before, when we talked about our unknown target function or ground truth target function, we presented it as a closed form function f of x. Now, in this case, our y value is a so-called deterministic function of x. Now, if you can have the same x that can be both a +1 label, a good credit risk, and a -1 label, a bad credit risk, now we introduce a probabilistic aspect. And so how we account for the different outcomes is using a distribution over class labels. And we model this as a conditional distribution probability of our +1, -1 label, y can be +1 or -1, given our input feature vector representation. So we said that we have our label instance pairs, our vector instantiations x, and our labels y. And these are now produced or generated, you can think of it mathematically, using Bayes' rule, as our probability that give us our feature vectors times our conditional probability y given x, our noisy target function. Now, you can think of a noisy target function as this deterministic target function plus some noise. And so the target function that you're after is just f of x is the expectation, the conditional expectation of your class label y given x. And this is our target function, but what's left over is noise. This is going to be our y value for particular x, and now we subtract from y our deterministic version of the function, f of x, and that's going to be our noise. So our deterministic target function is really just a special case of this noisy target function, p of y given x, that puts all of its probability mass on one of those label outcomes y, which is the y returned by the deterministic f of x. And so it's important to note that when we talk about our label instance pairs x, y, as resulting from p of x times p of y given x mathematically, well, know that these two are not the same concept. This concept, p of x, that's the probability that gives you the feature vectors. And you can think of this as scoring a notion of importance to the different vector instantiations. A vector instantiation that's more important will occur more frequently, have higher probability. This p of y given x, that is our noisy target function. It's the association of different labels, +1, -1, that could occur with the same input vector. So while mathematically this works because of Bayes' rule and the definition of conditional probability, they're not the same concept, these two probabilities. What you're trying to estimate in the case of noisy target function, you're trying to estimate p of y given x through expectation. What's the expected label given this probability of y given x, our conditional probability? So now we augment our anatomy of a learner using this noisy target function. So we have now an unknown target distribution, and this unknown target distribution governs the label noise associated with our unknown target function. So now we have an unknown target function with noise. Produces some training examples, and we have our probability giving us the importance of particular training example vector instantiations, as well as the out-of-sample point instantiations. And then, as usual, we have the things we control, the hypothesis set, the learning algorithm, the pointwise error measure, and indirectly, the final best hypothesis. And so there's a probabilistic nature of X and Y, and our goal is to learn our target distribution. The input distribution scores our inputs relative to the importance, as we said before, and we have our P of X and our P of Y given X, and what we're trying to learn is P of Y given X. That's what we're trying to learn the target function. Now, when you merge them by saying we're trying to learn this joint distribution P of Y of X comma Y, sometimes in the literature this is called a generative classifier. But this mixing of the two through Bayes' rule and the definition of conditional probability, it improperly mixes the two ideas. The two ideas are separately the importance of the feature vector and the noisy target function. There's a category of methods called generative classifiers where you're trying to mimic the association, the co-occurrence between vector instantiations and labels. And that's an approach to trying to build a classifier that mimics the process that gives you the associations. But these two, P of X, our importance score for the instantiations, and our noisy target function, those are two different concepts. Okay. So to say that learning is feasible, we talked about Hoeffding's inequality, and we talk about this idea of the coincidence or the tracking of out-of-sample error with in-sample error. And to be feasible, we had to strike the right balance between the size of our hypothesis set, M, the size of our sample, in-sample points, N, and our error tolerance, epsilon. And we said that if we can strike the right balance between these three competing factors, we can get in-sample error to coincide well with out-of-sample error. They're within some error tolerance, epsilon, within one another, and they do not violate that error tolerance very often. The probability is bound by a very small probability. So very infrequently will this violation happen. So we need then our final best hypothesis, G, to approximate well our ground truth target function. So this effectively means our out-of-sample error on our final best hypothesis is 0. That's what it means to approximate well the unknown target function. But this idea of the out-of-sample error for a final best hypothesis, G, we can't do that in practice because we don't know what that unknown probability is. We don't know what those values are out of sample. It's a theoretical concept. So what do we do in practice? Well, we get our out-of-sample error for our final best hypothesis, G, to be approximately 0, to coincide with our unknown target function. We do this by striking that balance as prescribed by Hoeffding's inequality for the union-bound case, and that means that E out for this final best hypothesis is going to be very close to E in for this final best hypothesis. Now, through the action of our learning algorithm, we drive in-sample error to 0. So if E in is very close to E out, and at the same time, E in is very close to 0, that means E out, which is very close to E in, is also going to be very close to 0. And we get E in to be close to 0 by minimizing our average in pointwise error through our learning algorithm, be that classification or regression. So to learn means that we can ensure both that out-of-sample error is close enough to En. That's guaranteed by striking that balance prescribed by Hoeffding's inequality in the union bound. And at the same time, we can make En for our final best hypothesis small enough. That's what it means to learn. It means we make in-sample error small, and we make sure that in-sample error is very close within epsilon of out-of-sample error. E-out is a theoretical construct. E-in you have control over. Okay, so to learn means to satisfy these two criteria. So we also talked about how feasible learning is for a hypothesis set of size m. And we've noticed when we select a weight vector, even for a two-dimensional weight vector, W is W1, W2 that we augmented with a W0. Well, if all the W's are real valued, this gives us an infinite number of hypotheses through which we have to search. So how is feasible learning for infinite case? Well, later on, we'll talk about a trade-off that we can make even if we have an infinite hypothesis space. Now, we'll do that with a complexity measure, and this complexity measure, as it gets larger in this graph, going to the right, our hypothesis is more expressive. It's more complex. This notion of bigger, m has a really large size. Now, if we make the complexity bigger, we see there's a relationship between in-sample error and out-of-sample error. In-sample error is going to decrease. Out-of-sample error will start to decrease because in-sample error tracks with out-of-sample error. But if we go too far with complexity, out-of-sample error starts to diverge. We'll learn about what that point is called when we talk about overfitting. And then as model complexity goes up, there's going to be a point that we can find strikes a balance called the VC dimension. And this VC dimension will give us a way to characterize a feasible learner in spite of our hypothesis set being of infinite size. So we'll do what we'll do with this framework of VC dimensions, complexity analysis. We see that as model complexity increases, in-sample error decreases, but at the same time as model complexity increases, at some point, the difference between in and out of sample error is going to increase. So we're going to stop before that starts happening, and that's going to be our VC dimension. And so this is what lies ahead, and this approach has a lot of power because it doesn't matter how elaborate your hypothesis is, it'll tell you whether or not learning is feasible with this abstraction of this aspect of the size of the hypothesis set, this abstraction. Okay, so that's what we'll have next time, but that's all we have for today. So we'll end here, and as usual, please stay healthy, stay safe, and I'll see you all on Thursday.